Alright, so for this week I chose to do problem number 29 in section 7.2, which asks us to take matrix A, which is 2, negative 2, 3, 1, negative 1, 3, 1, 2, 4, and the eigenvalues lambda 1 equals 1 and lambda 2 equals 3, and find a basis for the eigenspace found with lambda 1, and use the Gram-Schmidt process using those vectors to find an orthogonal basis for eigenspace 1. That's part A, and I'm going to do that one first. So, in order to find the eigenvectors, we have to take lambda 1 and place it into this matrix using the formulas related to eigenspaces. So with that, we would get A is equal to 2 minus 1 would be 1, then negative 2, 3. 1 minus 1 would be 0, excuse me, that is not correct, since the lambdas get plugged in on the diagonal. So the value would be 1, and then negative 1 minus 1 begets negative 2, and the third value ends up being 3. That looks nice. And then row 3 would be 1, 2, and 4 minus 1 is 3. Let me verify I have the right values. So I just went over the problem again. It looks like this value right here is supposed to be a negative. I copied that down wrong. I do apologize. So we set that all equal to 0 so that we can find the vectors. And simply adding the opposite of row 1 to row 2 and the opposite of row 1 to row 3, we would get the matrix 1, negative 2, 3, 0, with nothing but zeros in the remaining entry points. So from this, I'm going to let V2 equal S and V3 equal T. So V1 would be equal to 2S minus 3T. So from that, eigenspace 1 would be equal to S times the vector 2, 1, 0 plus T times the vector negative 3, 0, 1. So E1 is equal to 2, 1, 0 and negative 3, 0, 1. And they are linearly independent since vector 2 does not equal some scalar multiple of vector 1. Great, so we have our basis, which I'm going to write down up here. Just kind of keep it organized. Alright, and then I'm going to erase this work here so that we can find the orthogonal basis for these two vectors. Alright, so using the Gram-Schmidt process to find an orthogonal basis for this vector, the first vector of the new orthogonal basis for the Gram-Schmidt process would just be the first vector in the eigenspace. So V1 is equal to 2, 1, 0. Great. Now the second vector, using the Gram-Schmidt process, would be the second vector in the eigenspace, and subtracted from that would be the inner product of the second vector with the first vector over the norm of the first vector squared times the first vector. So the inner product of the second vector of the eigenspace with the first vector of the orthogonal basis would be, let's see, negative 3 times 2 is negative 6, and then 0 times 1 is 0, and 0 times 1 is 0. So the inner product of the second vector with the first orthogonal vector is negative 6. Now as for the norm of the first vector, that is the square root of the inner product of the vector with itself. So we would end up with 4 plus 1 plus 0, which just ends up being the square root of 5. But we have to square it. So this fraction right here ends up being negative 6 over 5. So if we plug in our vectors and our newfound values, we end up with negative 3, 0, 1 minus negative 6 over 5 times 2, 1, 0. And if we distribute this and turn this vector into 3 values with a denominator of 5, just for simplification, we end up with negative 15 over 5 times, or not times, but 0, and then 5 over 5 minus negative 12 over 5, negative 6 over 5, 0, which gives us the vector negative 3 over 5, 6 over 5, and 1. So the orthogonal basis for E1 is equal to 2, 1, 0, negative 3, 5, 6 over 5, and 1. Alright, so that's the first part. The second part asks us whether or not the eigenvector found with lambda equals 2 is orthogonal to the vectors in the original eigenbasis. So I'm going to erase this and save this up top here so we can find the next eigenvector and go from there. In fact, I'm actually just going to leave the eigenvector, or the orthogonal basis, down here. This next step should not require that much room. Alright, so for lambda equals 3, we end up with the matrix negative 1, because 2 minus 3 is negative 1, negative 2, 3, and then set that equal to 0, 1, negative 4, 3, and then 1, negative 2, 1. Alright, now this matrix is a little ugly. So if we take row 1 and add it to row 3, we end up with four, negative 1, negative 2, 3, and 1, negative 4, 3. Awesome. Then we take row 1 and add it to row 2, we end up with 1, negative 2, 3, 0, 0, negative 6, 6, 0, 0, negative 4, 4. And if we take row 3 and multiply it by, well, take this, reduce it to 1, and then take row 2 and reduce it to 1, and add the opposite of row 3 to row 2, we end up with the matrix, and I'm going to multiply this top row by a negative 1, so we end up with 1, 2, negative 3, 0, 0, 0, 0, and then 0, negative 1, 1. Awesome. So the only thing that trips this up here is we need to get rid of this 2 so that we can find our actual vector. So if we take row 3, multiply by 2, and add it to row 1, we end up with 1, 0, negative 1, then 0, 0, 0, then 0. And I'm going to multiply row 3 by a negative 1. So we end up with 1, negative 1, 0, 0, 0. Awesome. And if we let V3 equal R, V1 ends up being R, and V2 ends up being R. So eigenvector 2 ends up being just 1, 1, 1. Alright, now the final step is figuring out whether or not these two vectors are orthogonal to this vector right here. Now, to tell whether or not two vectors are orthogonal, you have to see if their inner product equals 0. So if we take the inner product of, alright, I'm going to let this be V1, this be V2, and the eigenspace 2 vector be V3. So the inner product of V1 with V3 would be equal to 2 times 1, which is 2, plus 1 times 1, which is 1, plus 0 times 1. And we end up with 3, which does not equal 0. So V1 is not orthogonal with V2. Alright. Let's see, or excuse me, V1 is not orthogonal with V3. I just realized I misspoke. So V1, let's try V2 with V3. So negative 3 over 5 times 1 is negative 3 over 5. Plus 6 over 5 times 1 is 6 over 5. Plus 1 times 1 is 1, and I'm going to set that to 5 over 5, just for simplification purposes. And if we simplify that, we end up with 8 over 5, which does not equal 0. So, none of the vectors in the original eigenspace are orthogonal with the third vector in the second eigenspace, which completes the problem.